NASA's Hubble Space Telescope has accurately measured the mass of the oldest known planet in our Milky Way galaxy. This ancient planet has a remarkable history, existing in a challenging environment. But what is this environment, and how did scientists manage to measure such an old planet? You can find out here. If you enjoy our videos, please support us by subscribing to Just Space and look forward to more exciting content in the future. Let's begin our journey through the vastness of the universe. PSR B1620-26b** is a pulsar planet orbiting the pulsar PSR B1620-26 in the globular cluster M4. It is located about 12,400 light-years away in the constellation Scorpius. This exoplanet is considered the oldest known exoplanet, with an estimated age of 12.7 billion years, almost 1 billion years after the birth of our universe in the Big Bang. It formed from a young sun-like star and is over 2 times older than Earth, which is approximately 4.5 billion years old. What's fascinating about this planet is that it orbits a unique pair of aging stars in the crowded center of a globular cluster containing more than 100,000 stars. So, how do we know this star has a planet? Well, before our Sun and Earth even existed, a Jupiter-sized planet formed around a star similar to our Sun. Today, 13 billion years later, NASA's Hubble Space Telescope has accurately estimated the mass of this distant and ancient planet. Hubble's observations reveal that the object has 2.5 times the mass of Jupiter, confirming that it is indeed a planet. Its existence provides strong evidence that the first planets formed rapidly within a billion years of the Big Bang, leading astronomers to suspect that there could be many more planets in our universe. The old planet has an extraordinary history, as it resides in an inhospitable region. It orbits a peculiar pair of aging stars in the dense core of a globular cluster. The discovery story ***. The story of this planet's discovery began in 1988 when the pulsar PSR B1620-26 was found in M4 by astronomers led by Donald Backer. This neutron star spins around 100 times per second, emitting regular radio pulses like a beacon. The white dwarf companion was quickly identified due to its interaction with the pulsar. As the two stars orbit each other every 2 years, astronomers later noted further anomalies in the pulsar, indicating that a third body was orbiting the pair. Initially thought to be a planet, it was also considered a brown dwarf or a compact star. The debate over its true nature continued into the 1990s until astronomers were finally able to measure the planet's actual mass. Through advanced observational techniques, they used Hubble data from the mid-1990s to study white dwarfs in M4. Analyzing these observations allowed them to identify the white dwarf orbiting the pulsar and measure its variability and temperature. Using evolutionary models developed by Brad Hansen at UCLA, astronomers estimated the masses of the white dwarf, the pulsar, and the planet. As the planet passed through the binary star system with an old neutron star and a white dwarf, gravitational forces created a complex arrangement of orbits. Eventually, the white dwarf was ejected from its original position and sent out into space by the larger planet. Simultaneously, the planet was thrown into a circumbinary orbit, a large path around both the original star and the neutron star. This new configuration of the planet, its sun, and the neutron star underwent what is termed a gravitational slingshot, allowing the newly formed binary star system to escape the dense core of the globular cluster into a less crowded region, reducing the chance of further stellar interactions. Over the next billion years, as the planet maintained a long orbit around the neutron star and its progenitor star, about 2 billion miles away, it witnessed the death of its progenitor star as it evolved into a red giant, shedding material to the neutron star. This mass accumulation caused the neutron star to spin increasingly rapidly, ultimately transforming into a pulsar that completes nearly 100 cycles each second around its axis. To put that in perspective, that's multiple times faster than a hummingbird flapping its wings. Once the red giant exhausted its gas, it collapsed into a white dwarf with a helium core, while the planet remained in its expanded orbit. How scientists verified its existence ***. Using Hubble data, researchers determined the age and mass of the white dwarf by analyzing its temperature and luminosity, which they compared to the wobble of the neutron star. Radio observations of the pulsar showed anomalies in its signal that couldn't be explained solely by its companion star. By using this information, scientists deduced the inclination of the white dwarf's orbit, allowing them to estimate the mass of the third body, which was too small to be a brown dwarf or another star. The planet's orbit and position within the globular cluster provide clues about its past. The white dwarf must have lost its gaseous envelope after the planet formed, allowing it to enter orbit around the neutron star. Additionally, the The planet's nearly circular orbit indicates that the mass transfer from the progenitor star to the neutron star occurred after the planet had established its orbit around the binary system. Stars that closely approach one another are rare in the Milky Way. However, such encounters are common in the dense central regions of globular clusters. It's likely that the neutron star has migrated into this system and captured the white dwarf during this process. About 1 billion years ago, the star captured by the neutron star evolved into a red giant, and it's believed that when the red giant formed, the companion star crossed the Roche limit, allowing for the exchange of material. This material exchange ceased once the star's outer layers, which were losing mass, were depleted, leading to the formation of the white dwarf. Since then, the two bodies have orbited each other. The long orbital path also makes the system more susceptible to gravitational interactions with nearby stars. The continued existence of the planet suggests that the stellar environment has remained less dense since its formation, as such a system would likely collapse back into a denser core within 1 billion years. Researchers can establish an age for the planet based on the current composition of the system. PSR B1620-26b***, often referred to as Methuselah is recorded in the Simbad database as PSR B1620-26b, even if this name isn't officially recognized. The name Methuselah is derived from the biblical figure who is known to be the oldest person mentioned in the Bible. Today, it's astounding to think that there are planets nearly as old as the universe itself. The most intriguing part is that we don't know if there are more planets with a similar age to Methuselah. Scientists believe that Methuselah may not be the last old planet discovered by astronomers, and who knows, perhaps one day they will find planets that are even older. Compared to Methuselah, the Earth is merely a breath of air, an unborn child. What do you think? Does the discovery of the planet Methuselah illustrate the vastness and mystery of the universe? Do you believe that, in the future, other planets older than Methuselah will be found, or do you feel that astronomers have already identified the oldest planet in our system? Share your thoughts in the comments. We're curious to hear from you.